Okay, so today we're going to be looking at how to do basic composite simulation in SolidWorks. This is for the MSE398 Composite Tube Design Competition. So first thing, you're probably familiar in SolidWorks with what we call solid geometry, which is three-dimensional shapes that have volume. For this project, though, we're going to be using what we refer to as surface geometry. So we're just defining surfaces that are still three-dimensional, but they have no thickness. And we're going to be using that to define our geometry and to run our simulation. So first thing, let's make a tube. So we're going to start with a sketch, draw a circle, and use the Smart Dimension tool to specify its diameter. Just for this demonstration, we'll do 2 inches. Now, if you don't have the Surfaces toolbar visible, you can go to View, Toolbars, and then scroll down, and you'll find way down here we have Surfaces. There are other ways to access these tools, but this is the most convenient. The tool we're going to use is the Extruded Surface. Just like the familiar extrude tool, it does an extrude in whatever direction you specify. In this case, we're going to extrude normal to our sketch plane, and as per the project description, we are going to specify the length of our tube. Okay, well, something went wrong there, so let's go and, exactly, units, important, 300 millimeters. Okay, so here we go, we have a tube. Notice that it has no thickness. Also notice that the free edges of the tube are colored blue. Now this is a characteristic of surface bodies in SolidWorks. Free edges will be colored blue. Internal boundaries, like between adjacent faces, will be black lines as you're used to seeing on other types of geometry. So we've got our tube. Before we go and start doing some simulations, we want to define certain regions on the tube. We know that we're going to be applying a fixture to one end where the tube is connected to the test apparatus. We know that we're going to be applying a load to the other end. So we're going to define where those ends are. So we sketch on a perpendicular plane to our first sketch, and we're going to draw 2 lines. Draw a line here and a line over here. You can look in the project requirements for exactly where these lines should be, where the ends of the tube are constrained, and interpret that however you think is appropriate. I'm just going to enter in some arbitrary values here for the sake of this simulation. Okay, so we've got our lines. We're going to go over to the Features menu, and under Curves, select Split Line. We're going to select the tube surface as the face, and the current sketch is already selected under the geometry. And now you can see we've got several different faces now that have been split up by the split line. Alright, so this is a great spot to save. So let's save our document as something useful. Okay, so we've got that, it's saved. If you haven't already done so, go to the add-ins and load SolidWorks Simulation, and we're going to go over to the Simulation tab and create a new study. This is just going to be a static study, so we can leave all the default settings, give it a name if you want to. And here we are. So if you haven't seen this before, there are a few kind of stages here that you'll want to take note of. First off, we have the geometry. This also encompasses the material definition, and we'll talk more about that in a moment. We have connections, so if it's a multi-body part or you're simulating loads or the behavior of an assembly, this would be relevant. It won't be relevant for, at least for now. Fixtures. This is how we restrain our model. Loads, that's self-explanatory. Meshing is how we discretize the model into finite elements to set up the simulation from a computational standpoint, and then result options will be visible once we have some results computed. So first thing, and most important thing for this lesson, is defining composites in SolidWorks simulation. Normally you can specify a material, but we're actually going to be specifying the layer by layer definition and orientation of the composite materials as well as what those materials are. So we right click, and rather than apply or edit material, we're going to go to edit definition. So here we have several options. We're going to select composite, and now we have this, this window that you're going to get very familiar with over the next few days. So a few things to note here. We've got the total number of plies or layers, and then we've got this window down here that shows each layer and how thick it is, what angle it's at relative to some reference, and the material that it's made of. Because we're using all the same material, we can set all plies same material and then select what that material is going to be. Now you'll have to define a new custom material. The data for what I'm using here, which is representative of the pre-preg carbon fiber that we'll be using in the lab, is available in the lab document. So you can look there, and defining a new custom material is fairly straightforward. If you don't already have a custom library defined, you can create one just by right-clicking on one of the material libraries and selecting New Library. Within that, you'll need to create a new category, and then within a category, you can create a new material. I've already done that, so we have this. One important thing to note is that the material definition described in the lab document is for an orthotropic material. This means that it has different properties along each of its axes, and that's very important for realistic simulation of unidirectional composite materials. So I'm going to apply this, close the window, and now that definition is going to be applied to every layer that we define for this setup. Okay, so from here we're going to start defining some different composite layers. They are going to be all the same thickness. Right now I'm just using a kind of placeholder value, an estimate. There will be a measured value provided in the lab document. So for now I'm just going to go with, let's say, 0.13 millimeters. Close to what we're going to be using, but maybe not exact. So we're going to do that for all current layers. Now if we create any additional layers, they're going to come in with the same definition, the same orientation as the last layer. So to make my design process a little, well, actually no, we're not going to do that. I was going to say we should put in the symmetric flag, but we're not going to do that. We're going to give ourselves just a little bit more freedom. So as a starting point, let's enter in some layer orientations. You can see now, based on the marks on the surface body, what the 0 degree reference is. Now, I would prefer for my own simulation to have the 0 degree reference along the axis of the tube, so that fibers running at 0 degrees are running in the direction of the tube. So I'm just going to check this, or rotate the 0 degree reference, and now that's exactly what we have. So we're going to throw in some different angles here. We're going to do 45 degrees, then minus 45, then another at 45, and then another at minus 45. So you can see the preview of the layer orientation updates as we change each of these angles. So you have a visual representation of what these mean. Okay, so we've got our material specified. It's that orthotropic material definition. We've got some layers defined. Now the tube itself is good to go. Because we only have one surface body, we don't need to worry about connections. We do need to worry about fixtures. The most basic type of fixture is fixed geometry. That just fully restrains whatever surface or edges you select. We're going to select this surface that represents where the tube is connected to the loading fixture, or to the support fixture. It may be relevant for you and your projects to get a more accurate simulation, to experiment with different types of fixtures or different placements of fixtures, but for now, this is all I'm going to do. Okay, so we have that fixture. We're going to apply a load on the end. What we're going to use here is a remote load. So what we do is we specify the surface that or edge that the load acts upon. We're going to define the position and orientation of this load in the global coordinate system, so we don't need to do anything here. For the location, we know that we drew the tube starting at the origin. We can confirm that if we just highlight here and see the origin indicated there in orange. If you note the direction of the global coordinate system, our tube extends along the z-axis. So we are going to place our load at a z value of 300 millimeters. That is the length of the tube. And off-axis by the amount specified in the project document, which I don't recall offhand, so we're just going to say 150 millimeters. It might be more or less than that, but you guys can confirm. This is just a demonstration. And finally, we are going to specify a load that is perpendicular to the off-axis direction. So you'll see in a moment what exactly that means. And the magnitude of this load doesn't particularly matter, so we can just do some reasonable value. Say 500 newtons. Okay. So we can see this preview now. And it's giving me an error. Oh, there we go. Okay, that's what we're looking for. So you can see that the load is oriented perpendicular to the tube, but off-axis. Now, for the project, the load is going to be acting at a slight angle. So in order to do that, you could define a different coordinate system. You could specify the load as x and y components of the load to get the correct overall angle. How you do that is up to you. Okay, so we've got our tube. The material definition has been created. We've got our fixture applied. We've got a load applied. Now we need to create a mesh. So the mesh is how, as I mentioned before, is how we discretize the geometry into finite elements prior to the simulation. The size of the mesh impacts the accuracy of the simulation, but also the runtime. So depending on what type of a computer you're using and what kind of effects you're expecting to find or observe in this simulation, you may want a coarser or finer mesh. I'm running on a fairly good computer, so I'm going to do perhaps a 3mm mesh size. That will take just a couple seconds to create, and now we can see here we've got this very fine mesh. You'll note that the mesh edges line up with any edges on the face or ends of the tube. Okay, so we've got everything defined. This is a great juncture at which to save the project, so we'll save it, and then we will run the study, and it will compute the simulation. This will take just a few moments in my case. All right. So by default, the first thing displayed is a von Mises stress plot for the first layer only. Now what we're going to do is switch this to the worst of all the layers. So we right-click on Edit on the stress plot, go to Edit Definition, and select Maximum Across All Plies. Depending on what you like to see, you can either leave it in the automatically scaled deformed shape, or show it at true scale, or specify whatever scale you feel like seeing. I usually like to visualize things with true scale deformation, but that's just preference. All right, so now we can see, well, what's happening with our tube. So first thing we want to think about is this load, is this deformation, this stress distribution reasonable given what we're trying to simulate? Because it's quite possible in all sorts of finite element simulations to set things up in a way that gives very unrealistic results. One of the ways that we can look at that is by taking a look at the displacement. So what we see here is that the tube does bend in the direction that we expect it to, but we can also see in this exaggerated displacement that the end of the tube is becoming non-circular. Now, based on the way that it's going to be set up in the loading apparatus, the end is going to be fixed over an aluminum cylinder. So there's no real way that it's going to deform in this way. So we should change our simulation setup to get something more realistic here. The simplest way to do that, I think, is to have the aluminum cylinder present. That's easy enough to do. So we don't even need to make a new sketch. We can use the same sketch. We're going to select our sketch, go to the Features menu, and create an extruded boss. We are going to specify that extruded body is, let's say, 0.75 inches long. And that's just because that's the same distance I used here. And we're going to offset this by the length of the tube. And we're going to set its direction so that it is within the initial surface body that we defined. Okay, so now we've got that. The surface body overlaps with that solid body. That's entirely allowed. There's no issues there in running the simulation. We go back to our simulation, and now we've got these warning flags. So we're going to look here, and we see, yeah, we've got this body in the simulation that has no material properties. So we're going to apply a material to it. Doesn't actually matter too much what we apply, but because that's what we're actually going to be using, we will say it's 6061 T6 aluminum. So now we've got that. Now we do need to worry about connections because we've got multiple bodies. So we're going to create a component contact. We're going to say bonded, and it's a global contact. All bodies that we have in the simulation should be bonded wherever they contact. That's a reasonable way to approach this problem because we know that we're going to be clamping the tube very tightly to the aluminum support. Okay, so now we've changed the geometry, so that necessarily means we need to recreate the mesh. We can probably use the same settings. Now you'll note that where we have these two overlapping bodies, we have this overlapping mesh. We've got a surface mesh and a solid mesh. They overlap, and the nodes are coincident. So these meshes are what we call compatible meshes. So the simulation will directly interface loads and deformations at each point in the overlapping mesh. Okay, now we run the study again. taking a bit longer now because we have many more mesh elements present in this solid body. Okay, so we can see already that the stress distribution looks slightly different. We can also see in the displacement plot that the end maintains its circular shape, which is the kind of behavior that we would expect. Okay, so now we can dig into these results a little bit more. First thing let's look at is the stress distribution. We can see that in general we have higher stress on the top and bottom of the tube, lower stress along the sides. Again, in general, we have higher stress near the fixed end and lower stress at the loaded end. We can also define a very handy type of plot called a factor of safety plot. So we right-click on Results and define factor of safety plot. So here, we're really only interested in the composite tube, so we're going to apply our plot to only the selected bodies, and we select the tube. We're going to use the Psi-Hill failure criterion for composites, and we're going to specify an upper limit for factor of safety, because we're not really interested in things that are very far from failure. We're interested in things that are close to failing. So we're going to say we're not really interested in anything past a factor of safety of 10. We also want to investigate the worst case. So not just the first layer or some specified layer. We want to see what is the worst factor of safety we're getting the whole way through. And that's all we need to do. Okay, so it seems that in this case, everything is above a factor of safety of 10. So there's two ways that we could approach visualizing this. First off, we can note in our display information here that the minimum factor of safety currently in the simulation is 29. So what we could do is go to our load, edit definition, and increase the load by something close, like something on the same order of magnitude as that factor of safety. So let's do, yeah, exactly that. How about increase this by 25? So we're talking about a 12 kilonewton load now. Now, because we've changed the loading, we need to run the simulation again. We haven't changed the geometry or the fixtures, so we don't need to recreate the mesh. We just need to rerun the simulation. All right. So you can see our stress plot doesn't look much different, except that the color map is now scaled quite a bit higher. So we can go back to our factor of safety plot. And now we have something interesting. So we can see that this lower portion here has a factor of safety just over 1, as we expected it would, because we increased the load by approximately the same magnitude as the factor of safety. And this is a linear elastic simulation, so all of our results should be linear. We can also see that the factor of safety is lower on this bottom face than on the top. Okay, so that's kind of an introduction for simulating composites. There's one more thing that I would like to demonstrate for you, and that is how to simulate a composite structure that has different regions with different numbers of layers. So what we're going to do is simulate, we're going to modify the simulation so that we have two sections of the tube, one section having more layers, one section having fewer layers. So we go back to the model panel, and there are a few ways to approach this. We could work with our existing surface body and split it into two. Another way to do it would be to define more split lines, and then we can use that to create offset or copied surfaces. Another way would be to directly extrude multiple surface bodies, and that's what we're going to do here just because we already have this set up in a convenient way. Well, actually no, we're not. We're going to define a split line, another split line, or modify the existing one, and designate different regions as entirely different surface bodies. So we go to the split line feature, edit the sketch, and we're going to throw another line in there somewhere near the middle. And this is just a demonstration. I'm sure in your design process you'll be much more methodical. Exit the sketch, and now we have several different regions. What we can do is create an offset surface. So here we have this offset surface. We're going to specify an offset of 0, which is essentially copying the surface. And we select the surfaces that we want to copy. So now if we look in our surface bodies menu, we've got the initial one, and then these two new ones. Now, why are there two? There shouldn't be two. Anyway, there is two, so what we're going to do is merge them. So we select both of them, and then we go to knit surface. Select merge entities, and now that's a single contiguous surface body. What we're going to do now is delete the overlapping section from the initial surface body. To do that, we're going to want to hide this new surface body and the aluminum solid body. So let's get those out of the way. And now we use the tool delete face. So we're just going to delete them. We don't need to worry about any of the patching or filling. Get rid of those. And it's gone. Now we can unhide those hidden bodies, and you'll see we now have this interface between two surface bodies that's highlighted blue, because this is not just the boundary between two faces, it's two separate surface bodies. Now when we go back to our simulation, we're going to have some problems to fix. Some of the things that we defined no longer reference what they should. So first thing, we have the composite definition here. We want to also have a composite definition here. So what we can do is select both of them and then right-click on the one that's already defined and go to Edit Definition, and now that's going to be transferred over to the new one. So the reason I closed out the Edit Definition toolbar there was to apply this composite definition, and now we can go back and change things just on one of them or the other or whatever we want to do. So let's do fewer layers here. Okay, so we've got fewer layers. We've got 4 layers over here. We've got 2 layers over here. We can see that our fixture is still in the right place, but our load is now referencing this face, so we're going to have to fix that. So we go to our load, edit definition, clear that selection, and select that face. Because we've changed the geometry, we need to recreate the mesh. And it's a good thing to check, at least when you're starting out, that the mesh elements do in fact line up at the boundary between your surface bodies. If they don't, there's a very good chance that your setup is wrong, specifically with the connections. You need to, whenever you have multiple bodies that are behaving as a continuous structure, you generally want to apply a global bonded contact. Okay, so we've got everything ready. Now we can run the simulation. Okay, so we see a bit different of a stress distribution. We've got Again, high stress near the fixture, but we've also got a high stress location near the boundary. And that kind of makes sense. We've got this region that's thinner, presumably weaker, and then transition to a thicker area. So around here, we would expect to see a stress concentration and then a drop in as we get into the more heavily built structure. For a factor of safety plot, we can look at that. Now recall that we selected only one body on which to display the factor of safety. We can change that by going back to the definition and reselect anything that we want to include. Okay, so now we've got a little bit more interesting of a structure going on, and that's where I'm going to leave it. So from here, it's up to you guys to figure out how you want to design your tubes. You can experiment with different layer orientations, you can experiment with different tube diameters as specified in the project document. You can remove or add material wherever you think it should be. Now pay attention to how much material you have available. There's only a certain a certain area of carbon fiber laminate that you'll be provided, so you'll need to figure out where best to position that. This really is a material distribution problem. Okay, that's it for today.